So according to De Moivre's theorem, cos x plus I sine nx, plus I sine x exponent n will be equal to cos nx plus I sine nx. And we need to prove that this is actually the case. So what we do is that if we are using mathematical induction to solve the question, we need to test for n equal 1. So test for n equal 1 means that from this first equation we've written, we'll fix 1 in place of n. So for n equal 1, we have cos x plus I sine x exponent 1 should be equal to cos 1 times x plus I sine 1 times x. And these two are actually the same equations, if you can see. So for n equal 1, we've seen that the equations are the same. Now, once this is the case, then we go and test for n equal k, and that's what we call the inductive step. So we assume that n equal k is actually also correct. So for n equal k, then we have cos x plus I sine x all exponent k will be equal to cos kx plus I sine kx. Now, we've assumed that this is true. So once this is true, then it means that the term after n equal k should also be true. So the term after n equal k will be n equal k plus 1. So here we say that n equal k belongs to a certain set T, where we'll be picking the values of n from, the same for n equal 1. So now we also go and test for the n equal 1. That's the next value after n equal k. So for n equal 1, that's what we actually proved. So we have cos x plus I sine x exponent k plus 1, and this should be equal to cos k plus 1 times x plus I sine k plus 1 times x. So this is what the De Moivre's theorem says. So from here, we are just going to prove. You can use the left side to prove for the right, or use the right to prove for the left. I would like to use the left side to prove for us to obtain the right. So from the left-hand side, so from the LHS, we have that cos x plus I sine x all exponent k plus 1. This is the same as writing it as cos x plus I sine x exponent k times cos x plus I sine x plus I sine x exponent 1. Now from the inductive step up here, we know that cos x plus I sine x equals this. So we'll just replace this with this one. So we are going to have, let me move back. So we have cos kx plus I sine kx, put that in a bracket, multiplying cos x plus I sine x. Now we can actually multiply, so we use cos x to multiply cos kx, and we expand the brackets basically. So cos x, let me write that this way, cos x times cos kx is going to give cos kx cos x plus cos x times this will give I sine kx cos x, then plus, we now multiply with I sine x, that'll give I sine x, then cos kx, then plus I sine x plus times I sine kx is going to give I squared sine kx sine x. Now there are a few things we can do. We have cos x, cos kx plus, okay, so I squared is the same as -1 from complex numbers. So we'll just have to replace I squared with -1 from here. So let me say negative, and I'll come and write sine kx sine x. Then I group all the imaginary parts of the complex number. So I will say plus I in the brackets, then sine kx cos x for this side, and then for this side I'm going to start with plus cos kx sine x. Okay, now we can rewrite this generally as, I'm just rewriting the same thing, but I want to take away the positive sign from there. So cos kx minus sine kx sine x plus I in the brackets sine kx cos x plus cos kx sine x. Now from angular addition in trigonometry, we know that cos A plus B is equal to cos A cos B minus sine A sine B. Now when you look at the equation we have at the top here, if you replace x with A and then kx with B, you'll see that this follows the same idea of cos A plus B. What this means is that cos x cos kx minus, I'd rather write sine x, then sine kx is commutative, so it's no problem, will be equal to cos x plus kx, which is the same as cos, you can just factorize x out, so it will be the same as this. And also from trigonometry, we know that sine A plus B is equal to sine A cos B plus cos A and then sine B. Now when you look over here from this side, the imaginary parts, you can see that sine kx cos x plus cos kx sine x follows the same idea of sine A plus B. What that means is that this is the same as sine x plus kx, and then this can also be written as sine k plus 1. You factorize x out. Now the original question, we're using the left hand side to prove to obtain the right hand side. This is what we are trying to break down. So it means that cos x plus I sine x all exponent k plus 1 will be equal to this, that's the row part, and the row part is cos k plus 1 times x plus I sine k plus 1 times x. And this is exactly what we wanted to prove. What it means is that n equal k plus 1 also holds or belongs to the set T for De Morgan's theorem, and this is what we've been able to prove. So don't forget, from this side we're saying that if you fix in k plus 1 in place of n, then we are supposed, from here, then it means that you're supposed to get this, which is exactly what we've had here from the proving that we did. Now the second part of the question said that we should deduce for all positive integers n equal p on q, the result also holds. So what we just do is that from the original question we had cos x plus I sine x all exponent n to be equal to cos nx plus I sine nx. So now if n is equal to p on q, then it means that we can rewrite it to be this way: sine x all exponents p divided by q, and then this will be equal to cos p x on q plus I sine px all divided by q. Now what we should know about this is that if the complex number has an exponent of a fraction, then it means that the denominator is the number of roots that we can find for the complex number. So if, let's say, it was maybe 3/4, then it means that the complex number has 4 roots. In this case, it's Q. What it means is that this complex number has Q roots. So in order to be able to compensate or create room for us to have all the other roots of this particular complex number, we need to recognize the idea that trigonometric functions are periodic functions in case of both sine and cos. And sine and then cosine and then sine have a period of 2 pi. So we have to integrate the 2 pi into the formula, and then we are done. So cos x plus I sine x, all exponent p on q. In order to compensate for all the other roots, we'll rewrite it this way in terms of De Moivre's theorem. So we have p into bracket x plus 2 pi k, all divided by q, plus I sine p into bracket. Just repeat the same thing that is in the brackets, the angle, all over q. Now, so this will create room. We'll take different, so k can take values from 0 throughout to q minus 1. That's the values it takes. Okay, so k will take values from 0, beginning from 0 throughout to q minus 1. And by the time you get to q minus 1, you have all the possible roots. So that is how we solve, we prove De Moivre's theorem using the principle of mathematical induction. So thank you very much. And yes, n equal p over q does hold for De Moivre's theorem. Thank you.